Okay, Algebra 2, taking a look at section 11.3. So 11.3, talk about the probability of multiple events. Okay, so basically what happens when we have more than one thing going on. So we're not just talking about picking one thing out of a certain amount anymore, where it could fall in different categories or whatever that could be. We're talking about we're going to pick out one and then pick out another thing. Okay, so we're talking about multiple things that are going in. Now there are a couple of key things we start considering in here. Okay, we start talking about independent and dependent events. Okay, independent events have no influence, so there's no influence on what can happen to the next one. So from one to another, there's nothing that's going on. Dependent events are going to have some sort of relationship that occurs with it, some sort of influence, that this happens and then this can happen. So there's some sort of influence. So we have influence here. Okay, when we talk about independent and dependent events, we talk about the probability of A and B happening. Okay, so the probability of A and B happening. So if we come up here, I'm just going to write it so you can see here. For independent events, probability of A and B, I'm going to use my symbol for and, once again going back to our intersection of sets. So A and B happen. We're going to take probability of A times probability of B. Once again, there's no outcome change here. This could happen if we pull a number out of a hat, throw it back in, and then pull out a second number. There's no outcome change that's happening in here. We have two separate events, and we talk about each one being independently done. On the next one, we have influence, probability of A and B happening. Here we talk about the probability of A times the probability of B less A. Okay, once again, we have some sort of change in outcomes. You know, if I pull a marble out of a hat and now I keep it in my hand, and there was 25 to start, now there's only 24 marbles left in there. So this outcome has changed somewhat for the next event. Raffle tickets are a big thing on this. When they pull one out, those total outcomes change in there. Now, once again, there's a cumbersome number rule that kind of eliminates some of this, depends upon how many numbers are in there, to where you could treat them as independent. But that is more advanced probability than what we're getting into here. We're looking at the basics and just kind of getting you in that mindset of the difference that could happen within. Now, this is when we talk about both events happening. We have this and this happening. Other topics we start talking about are whether we have things that are mutually exclusive or mutually inclusive. Okay, so mutually exclusive and mutually inclusive. Okay, so with mutually exclusive events are basically two events that cannot happen at the same time. Okay, so if I roll a number cube and flip a coin, they don't have anything, there's no influence on here. They're exclusive. There's no overlap that could possibly happen in here. Okay, so no overlap. Okay, we can't have anything in common. Okay, no common. Okay, when we talk about mutually inclusive, now we're going to talk about that there could be some parts that are common, okay? Some overlap, okay? Where we have some where it could possibly fit in this category, or it could go in this category with what's happening. A lot of these kind of deal with that Venn diagram. So if I draw a Venn diagram here, we see that we have an overlap in that center. If I draw a Venn diagram here, we see that we have no overlap with those two parts that go in here. What we start relating to on these problems is we start talking about probability of A or B happening. Okay, so the probability of A or B happening. So I'm just going to come right below here for mutually exclusive, and I'm going to say, so if I have the probability of A or B happening, once again my union symbol for my or right here, we would look at the probability of A plus the probability of B. Okay, so we would see that we would have the sum of the probabilities. One of the biggest things to remember is and means multiply, or means add. Instill that, and you will be doing fine when you start seeing these. Okay. Coming right here, the probability of A or B. Once again, we would talk about the probability of A plus the probability of B minus the probability of A and B. Okay, so if you consider this, if I had to consider all these probabilities, if I took all of A and then I added all of B, I now added this middle part twice. So that's why then we take that out. Now do realize a lot of times on these mutually exclusive, mutually inclusive, you did it last chapter when you looked at the, last section, when you looked at the probability of red or blue marbles. Okay, we just said, well, there's how many red, how many blue, added that together, then put it over the total. Well, we could have looked at adding each of those fractions separately, and we would have had this right here. That's kind of where this goes into. There's going to be times we're going to use the formulas, times where we won't use the formulas. It all kind of depends upon how we can see the problems and how we can work through them. So let's look at number 10. Number 10 asks us to consider whether the trials are dependent or independent. So a month is selected at random. A day of that month is selected at random. So we're going to select a month, then a day of that month. Okay? So if we consider this, this is going to be an a dependent. Okay, this is going to be a dependent event. Now, why is it dependent? Well, think about February. Okay, if I selected February, that means I could only select 1 through 28 for the day, or a possible 29 on a leap year, but I can't have 30 and 31. So these outcomes here are influenced somehow by which month we select. Once again, January has 31 days, but April only has 30 days. So it's something just to be considering in here, that this month is going to have some sort of influence on this, thus making it dependent in here. On number 12, number 12 says the color of a car and then the transmission. So color of car, then transmission of the car. So if we think about this, car does not have an E at the end. Let's ignore that. The color of that car could be blue. Well, do all blue cars have manual transmissions or automatic transmission? No, there's no influence here. This color does not deem anything to what this outcome can be. It could be either or in any case. So we see that these are independent then. Okay, independent of each other. And then we could work with them as we were to consider what's happening. Number 18. Number 18 says two fair number cubes are rolled. State whether they are mutually exclusive, inclusive. You know what's going on here. So we're going to roll two number cubes. Okay. And we want to try to figure out, once again, the sum is a prime number or the sum is less than 4. So sum is a prime number or the sum is less than 4. So if I consider and if I look back to what I had going on, we had this chart that we did last section. Once again, if you remember this, we had that sum chart in here. If we consider what's going on here, let's come with a highlighter this time. We see that the sum is a prime number. So if we go to our prime numbers, we see that this is a prime number. 3, 4 is not, 5 is, 6 is not, 7 is prime, 8's not, 9's not, 10's not, 11 is prime, and 12 is not. So we see that here's all our prime numbers, okay? And then now, if we come with a different highlighter and we look at what's going on, it says the sum is less than 4. So So if I go less than 4 would be 2, 3 right here. If you notice, I highlighted these twice. So we see that that outcome, that possible outcome, is coming in both of our cases. So that means we are not mutually exclusive. We are mutually inclusive. Okay? That we have some sort of inclusion. Some of these outcomes appear with these outcomes, or these outcomes appear with these. That's what really relates to that overlap. Once again, we have two separate events we're doing, but we're just looking at the sum overall. So one of the relationships we start seeing back in between independent and dependent is we see that the events are completely separate. We have this happening, then we have this happening. We have two complete separate ones. Here we have two things that are making up one event, the sum. And then that sum could break up into different categories as we start looking at. And that's where that relationship kind of really starts developing in between here. Let's look at number 25. Okay, so on number 25, 26. You can do 25 for some practice if you want. Number 26 here, it says, a standard number cube is tossed. Find the probability that it's 4 or even. Okay? Well, we could work with this common sense wise, or we could use our formulas. Okay? A couple different ways we can consider this. If we were to use our formula, we're looking at what's the probability of 4 plus the probability of even. Once again, the or is plus. But wait, 4 is also even, so we got to subtract off the probability that it's 4 and even. Okay? So probability of a 4 is 1 out of 6. So there are 6 outcomes on a number cube. One of those is a 4. There are 3 out of 6 that are even. We could have a 2, a 4, or a 6. And once again, because 4 and 6 are even, 4 is an even number that is in both of these, so that is a 1 out of 6. So we see that we get 3 out of 6, which is 1/2. Now, common sense wise could tell you, if I have the numbers 1, 2, 3, 4, 5, 6 that I'm rolling, and I want a 4 or an even when I roll. Well, I want a 4, an even. Notice I just circled this one twice, but if I look at everything I circled, was a total of 3 out of 6 total outcomes. Notice 3 out of 6 for that 1/2. A lot of times on those mutually inclusive, mutually exclusive, common sense could help us tremendously with some of those, and we wouldn't have to look at those formulas, but this is how that formula does work in this situation. Number 32. Number 32 says a multiple choice test has 4 choices for each answer. Suppose you make a random guess on 3 of 10 questions. What is the probability that you'll answer all 3 correctly? So I got 3 questions, okay? And I'm going to guess on each of these. Now, if I guess on this one, there is no influence on this one. There is no influence on this one. So I have a 1 out of 4 chance to guess correctly on the first one. A 1 out of 4 chance to guess correctly on the second one. And then a 1 out of 4 chance to guess correctly on the third one. Okay, once again, if we think about this, we're multiplying because we have separate events, and we want all of these things to happen as we're looking at this. Okay, it's not asking one or the next or the next. It's saying we want to have 3 correct answers here. So there would be a 1 in 64 chance that if you had 3 multiple choice questions that only had 4 answers, that you could actually guess and get all 3 of those correct. Okay, and we'll start looking at this problem here a little bit later in our chapter when we talk about binomials. Okay, and a binomial distribution of being one or the other, right or wrong as we start looking at these. Let's look at number 37. Okay, so number 37 says a jar contains 4 blue marbles. So 4 blue, 2 red. Suppose you choose a marble at random and do not replace it, and then you choose a second marble. Find the probability of each event. We want the probability of a blue and then red. So probability of blue and then red. You notice, and then. So we want one event and then the next to happen. So we got two different events. We're not looking at multiple things within one event. We have two completely separate events going on. That's why we're multiplying. It's like these were separate questions. Back here, we had one row with different things that we were discussing within here. That's why it's that or. That's why it was a mutually exclusive, mutually inclusive event. Here it's different events that's happening. Considering this, probability of blue, so probability of blue times probability of red less, I'm going to go blue right here. Okay, once again, without replacement. Okay, so that means that total that was in the jar changed somehow. So we're talking about some sort of dependent event that's going on here. So if we consider probability of a blue, there are 4 out of 6. Now we want to pull out a red. Okay, so there are 2 reds in here, but we only have 5 of them left. Okay, so this is kind of like, on The Price is Right when they do the 3-strike game. And they put in the 5 numbers for the card, and they put in the 3 strikes. As you pull out one number, well, now you have that number that's taken out. Well, now those chances for those strikes start getting a little bit higher, because originally there was 2 out of 6 here, and now there's 2 out of 5 chance to pull out a red. And so this is where games are developed. So once again, the house wins more often than not. So now if we multiply this, simplify this, however we want to look at this, we get 4 over 15 would be our final probability right here. And that's what this section takes a look at. So once again, pay attention to that word and or. Also within the description, try to figure out, do you have multiple things going on within one event, or are you talking about 2 complete different trials that you're working with? So those different trials, that's generally where that multiplication comes into play versus that addition. Now, it's not always like that, so don't quote me that that's how it has to be, but that's a nice indicator that we can start looking at.